So what would happen if you have two waves that run into each other? Well, when that happens, we have a principle that we call superposition. And so that's what we're going to start off this video talking about. The superposition principle says that when two waves pass through the same point, then the displacement of that point is the arithmetic sum of the individual displacements. Here's what we mean. Here in this figure, you have two pulses that are moving towards each other. One is a crest and the other is a trough. They're moving towards each other. When they reach the center, what do? Well, the point, that point where they meet is going to have a total arithmetic sum of 0. Here's what I mean. Let's say that this has an amplitude of plus a, and this pulse has an amplitude of minus a. Well, on this point here, it's going to have a displacement of plus a plus minus a. In other words, 0. So it has 0 displacement, therefore it doesn't move. There is no wave. But the energy is still moving in the same direction. This crest is still moving to the right and the trough is moving to the left, which means that after they hit that point, they're going to carry on, the crest still moving to the right and the trough moving to the left. Now this, what happened here when our entire wave dropped down to 0 is something that we call destructive interference. Interference is this process of waves overlapping waves. Basically, you can think of it as one wave interferes with another wave. They get in the way of or overlap each other. Okay, so that's an example of destructive interference. But here's an example of the opposite, where you have two crests moving towards each other. Incidentally, you would get the exact same thing if you had two troughs moving towards each other. If this crest has an amplitude of plus a and this crest has an amplitude of plus a, then here, when they meet at the center, you're going to have an amplitude of plus a plus a. Positive a plus positive a. And we know that from the superposition principle, two waves are the arithmetic sum of the individual displacements. So that means that my total amplitude is positive 2a. But then as soon as they hit that point, the waves keep moving on and they move away from each other. So that is the superposition principle. Now here is another more dramatic example of the superposition. In the leftmost figure over here, figure A, you have two waves that look absolutely identical. They have crests at the same time. Let me pull up a highlighter here. They have crests at the same time. And they have troughs at the same time. I'm moving my pen all the way down here. So all of the crests and troughs happen simultaneously, which means that whenever you have a crest on top of a crest, you get double the amplitude for your total wave down here. Now, figure B, here you have a crest that meets up with a trough. And that's what happens every time, which means if you have a crest, which is positive A, and a trough, which is negative A, they add up to 0. You get absolutely nothing. So A would be constructive interference, B would be destructive interference of entire waves. Now C is a little more different because here you have a crest that meets up with, excuse me, I don't think I drew that quite straight. There we go. A crest that meets up with a 0 point. A crest plus 0 would be the crest. I see what's going on here. There we go. 0 plus the crest, positive A, would be positive A. And here you have a trough plus 0 gives you a trough. Crest plus 0 gives you a crest. So on. So anyway, what's going on is we are adding the amplitudes of the two waves together. And in this case, you get almost the same wave, just slightly shifted in a different phase, if you will. Now, standing waves can occur when you get interference in such a way that the wave doesn't appear to move. It looks like the wave is holding still. Now, this happens when both ends of a string are fixed. So you have this case here where the person's holding one end and the wall's holding the other end, and it's fixed. Now, in that case, the only time you can get a wave that actually appears is when you have one of these very specific standing waves. Now, let me define a couple things here. When you have these standing waves, you're going to have either a node, which a node would be this point here, and if you were to watch this node, it would appear as if it is never moving. And I'll show you one of those in just a second. Then you also have an antinode where you get the largest amount of movement and the string varies from positive A to negative A. And then you get what are called harmonics. Harmonics are the different possible standing waves. And you can differentiate one harmonic from another using the harmonic number. The harmonic number can be found by the number of antinodes. So in this first one, you see there is one antinode. So this is n equals 1. This also happens to be known as the fundamental frequency. It's the most basic harmonic with only one antinode. Now here you have two antinodes. So that is going to be the n equals 2 harmonic. Here you have three antinodes. So this is the n equals 3 harmonic. Let me show you this a little bit. Here's a website that, that really illustrates this well. You can note this and look at it yourself. I'll include it in the notes on Falcon Online. But I've got it going right here. This is what we've got. So we're looking at a wave on a string, first harmonic. Okay. So the length of the string is, of course, from one end to the other. But notice how this is only one crest or one trough. There is no trough or crest associated on the other side. So that's only half of a wavelength. I'm going to note that here, that the length of the string is going to be 1/2 of a wavelength. Since this is the n equals 1 harmonic, we're going to label this as wavelength 1. Well, and this tells us that wavelength 1 is going to equal 2L. Okay, come back here. Let's go to the second harmonic. This is what the second harmonic would look like. So you have an oscillation where you have two regions, or two antinodes, that are oscillating between plus A and minus A, and there's one node in the very center. Now, if you look at that, that's an entire sine wave. In other words, that is one full wavelength. So the length of the string is equal to the wavelength. So I'm going to say length of the string is equal to the wavelength of the second harmonic. I'm rewriting this on purpose because I'm going to come back and do something interesting here. Oh, sorry. That's where I want to be. Now let's go to the third harmonic. This is what a third harmonic would look like, where you have three antinodes. Now the first and second antinode would be one full wavelength, but then you have that extra antinode, which is just a half a wavelength. So the length of the string would be 1.5 wavelengths, or 3/2. Okay, So if I rewrite this, excuse me, that would be 3. Wavelength for the third harmonic would be 2L divided by 3. Now let me come back here to the second harmonic briefly, and I'm going to add something here. I'm going to add a 2 on the top and then divide it by 2 again, so I haven't changed the number at all. Well, what happens? On the top with the first harmonic, you get 2L, which is basically 2L over 1. The wavelength of the second harmonic is 2L over 2. The wavelength of the third harmonic is 2L over 3. And so I get that the wavelength of the nth harmonic is just 2L divided by n, where n is your harmonic number. Pretty cool. And by the way, harmonic number can be any number, 1, 2, 3, 4, so on. But it has to be a whole digit, whole integer. It cannot be a fraction or decimal. You can't have a half a harmonic. That doesn't make sense. Okay, now I want to look at something else here, and that is the frequency. Let's not use green. I already used green. Let's go to blue. So we know the wave equation says that the velocity of the wave is equal to the wavelength times the frequency. Well, if I solve for the frequency, I get that the fundamental frequency would be speed of the wave divided by the fundamental wavelength, which we know now is 2L. If I do the same here, frequency of my second harmonic would be the velocity over the second harmonic's wavelength, which is 2L over 2, which would be, if I fix the improper fraction, that's 2 times V over 2L. Well, remember V over 2L, we just saw that. So F2 is equal to 2 times my fundamental frequency. If I do the same thing for F3, that's velocity over 2L over 3. Fix the improper fraction, that's 3 times V over 2L. Hey, same thing. F3 equals 3F1. So that tells me that the frequency of my nth harmonic is just n times the fundamental frequency. And all of that is summarized here on this slide, where the wavelength of the nth harmonic is just 2L over n. L is the length of the string, n is the harmonic number. Frequency of the nth harmonic is n times the fundamental. And I will add that the fundamental frequency would be the speed of the wave divided by 2L, where 2L is just the fundamental wavelength.